I wanted to start out with an overview for how our material is going to be covered. The first few chapters are going to be concerned with particles and systems of particles. And what it means by particles is not like a grain of sand or something. What we're talking about is where forces are concurrent. They're coming together at a point, and this means that whatever we're looking at, the motion it's not going to be rotating, okay? So when we don't have to worry about rotational motion, no moments of inertia, no torque. So this is kind of the simple first step at motion. The next piece is going to be looking at rigid bodies, okay? So everything from chapters 15 to 18 is looking at rigid bodies, and this is where we're going to have forces that are no longer concurrent. And this will cause rotational motion, so we'll look at moment of inertia and those rotational things. These are fairly similar, okay? So we'll have forces with particles and forces with rigid body. We'll have energy balances with particles and then energy balances with rigid bodies. So 1/2 mv squared, and then we'll have 1/2 I omega squared added onto that. Kinetic energy from rotation as well as translation. The very last chapter is mechanical vibration. So this is going to be looking at some more springs, which goes into materials analysis, finite element analysis, so that F equals Kx equals ma. That's important stuff, and it's important for more reasons than just understanding a simple spring. The other way to divide this material up is kinematics and kinetics. Okay, so these are two different ways to analyze motion. Kinematics. This is chapter 11 is going to be kinematics, and what this involves is just the very simple relationships of v equals dx dt, a equals dv dt. We're going to be just using some calculus to go through the relationships between position, velocity, and acceleration. And this is without reference to forces. Okay, so no free body diagrams, no statics, just pure calculus to relate velocities and accelerations and positions. The next step is to use some kinetics. Okay, so kinetics, this is where we're going to start looking at adding up forces. So we'll draw free body diagrams just like you did in statics. And the difference there is that these forces are not going to add to zero. The forces will add to a motion, how the object is accelerating around. And then we will relate kinetics to kinematics. So when you solve for a force and then you figure out what acceleration is going on, well, you can take that acceleration and you can then calculate velocities. You can calculate what the position is 10 seconds in the future. So it's all related, but that's pretty much how it's going to be organized. So particles, rigid bodies, kinematics, kinetics. We'll start in 2D and then we'll go to 3D, and that'll be the overall flow of the course. 11.1, rectilinear motion of particles. Linear, we're talking about straight line motion and a rectangular coordinate system, just regular old XYZ, no polar complications yet. Just to simplify this to the main ideas, it's going to keep coming back to this chart of equations. And this chart of equations comes from the basic definition for velocity of dx dt, change in position versus change in time, kind of like miles per hour. And the definition for acceleration. So acceleration is change in velocity with change in time. And all we're doing is we're going to be plugging equations into these two relationships and rearranging these a little bit. Three different scenarios we'll go through. The first scenario is where we have something that is dependent on time. The second scenario is where we have something dependent on position. And the third scenario is where we have something that's dependent on velocity. Let's just walk through this first scenario, and I want to make sure everybody's clear on what the symbols up here mean. When you see these parentheses around, this is not acceleration multiplied by time. We're talking about an equation here, okay? So whether you say this, or maybe I should just write acceleration is equal to, and it's going to be equal to some equation, okay? So this nomenclature, it's not multiplied by time, it's just, this is a whole equation. So we have acceleration is change in velocity over change in time. And since these two are both time dependent, you might as well put those on the same side of an equation. So we're going to group everything that is time dependent over here, leave the velocity on the other side, and we can integrate this to figure out how velocity changes with time if we have acceleration changing with time. So we're just going to plug an equation in here, okay? So we're plugging an equation in. We're grouping all of our times together, okay? So instead of here, we have this whole equation that we're putting in here, and we're integrating it to find velocity's dependence on time if we know acceleration's dependence on time. Okay, here's the next scenario. We're going to look at acceleration as a function of position. If we come up to our standard definition of velocity and acceleration is dv dt, what we want to do is we want to get rid of our time dependency. Let me grab a different marker here. Okay, so we want to replace dt, and we want to get something that is dependent on position instead. And how we do that is through the chain rule. You remember how to do the chain rule from calculus. We're just going to multiply dv dt by dx over dx. Why do we do this? Well, dx over dt, that's our velocity, okay? So by making this little substitution, we've gotten rid of time, and now we end up with an equation for acceleration that is only dependent on our position. Okay, so once we have acceleration as a function of position, we can now plug in an equation where we have a bunch of x's instead of a bunch of t's in there. So the two basic equations for acceleration, we have acceleration equals dv dt. We also have acceleration is equal to v dv dx. So remember this v dv dx. This is a big deal. Once you have this, plug in your acceleration, okay? So instead of acceleration, we now have this whole equation. And you can group everything that has x's together, group everything that has v's together. So I'm going to put all the x's on one side. So again, this is our entire equation that we're going to plug in here and just integrate it. And once we integrate this, we can see how velocity changes with position, as well as seeing how acceleration changes with position. So it's very similar to what we saw before. We're just using integration and taking derivatives to go back and forth to see how everything's related to one another. The third scenario, something where we have acceleration as a function of velocity. Once again, we have an equation. This time the equation has a bunch of v's in it instead of a bunch of x's in it or a bunch of t's in it. This would be like for a drag situation, moving through water or moving through air. Okay, start with that basic equation. Acceleration equals dv dt. Okay, so this is one acceleration relationship. The other equation is acceleration equals v dv dx. Okay, once again, we're not multiplying by velocity. This is just indicating that we're going to be substituting an entire equation over here, okay? So instead of just equals a, we're going to have equals some big equation, okay? We're going to put in this entire chunk over there. Rearranging this, putting all of the velocities on one side for time, or all the velocities on one side versus position. This one ends up being a little bit trickier because you have your equation in the denominator. So these can be a little bit tricky to integrate depending on what kind of a system you have. But this is what it's going to look like. So you're going to have just some equation that you plug in here. Okay, so this is a whole equation that you plug in. And then you can look at velocity as a function of time, or position as a function of velocity, when you start with acceleration as a function of velocity. So we're just going back and forth between velocity, acceleration, and position for all of these guys. And there's a whole bunch of different ways to rearrange these initial basic definitions for what acceleration, velocity, and position are. Take one more look at this overview for all the relationships we're going to be using, and you might want to print this little table of equations out and just have it in front of you as you're working through your homework. Okay, so here's an example using the first scenario where we have a problem involving something changing with time. In this case, we're given position as a function of time. So here's our position of a particle, there's time in here. So x is expressed in meters, time in seconds, and we want to know the time, position, and velocity when acceleration equals 0. The first thing to do in these problems is to walk through and get equations for position, velocity, and acceleration. If we have one of these equations, we can figure out the other ones, either taking derivatives or integrating. Okay, so if we start out with position, velocity is dx dt. Okay, so we're just going from 10t to the fourth to 40t cubed to acceleration is 120t squared. Okay, we're just going through derivatives. Or if we started with acceleration, we could go the other way too, right? We can take integrals of things. You'd have to know boundary conditions and constants of where things are starting and stopping, but you can walk from one to another just using calculus with this. And it really is just these simple equations of velocity is dx dt, acceleration is dv dt. Once you have equations for how everything is changing with respect to time, then you can go through and start answering the rest of the problem. So when is acceleration 0? That's part of it. Take our equation for acceleration, and we're just going to set that equal to 0. So we have an equation with one variable, t squared, so we're going to have to just use a quadratic formula here, and we can solve for the times where this equation is 0. Once we have those two times, we can figure out the position and velocity at this point too. Okay, so we have our times, we have an equation for velocity, and we're just going to plug in what we found for time into this velocity equation. Okay, so we have two different times we're looking at. That gives us the velocity that is happening at this point. Same thing for position. Okay, so we have our equation for position, and we're just going to plug in what those times are. You're just plugging in numbers and solving for what the position is. These equations, sometimes it's good to look at these on a graph. Okay, so here's our position. You can take the derivative. Here's your velocity. Here's your acceleration. And it asks what is happening when acceleration is 0. We're looking for where this green line crosses 0, and at the same time, where's our position, where's our velocity. So just look at this graph, see where everything is crossing 0 and what's happening, and you can plug in numbers to equations. So that's all that there is to it for the time scenario. Back to our table of equations. So that was an example for acceleration as a function of time. Now let's do this second scenario and see an example of acceleration where we have everything as a function of position instead. Here's an example for the second scenario. We have some kind of an acceleration, and this equation is dependent on our position. And these problems would involve things like a mass on a spring. So force equals kx equals ma. So a is equal to, we have our spring constant over the mass, and x would be the compression of the spring. So the acceleration of an object with a mass of 1 kilogram is given by this equation here, where x is the compression of the spring, x and t are expressed in meters and seconds. If the spring undergoes a maximum compression of 0.05 meters, so this is going to be the amplitude of how far this guy is stretching around. Okay, after starting with the maximum velocity, so we're just getting a lot of boundary conditions here. So there's our max velocity, our max compression, and we want to figure out what the max acceleration is and what our spring constant is. I just wanted to talk through where maxes and mins and zeros happen in this system again, and thinking about the forces is more of a chapter 12 thing, but just so you can get an idea for why we would care about max and min and how these are related to one another. Okay, so an object on a spring, it's going to come to the very top, stop before it starts falling back down, and then at the bottom, it's going to stop at the bottom as well. So velocity is 0 all the way at the top and all the way at the bottom. And then in the center of this thing, that's where the maximum velocity is going to happen. So it starts falling, the spring is pushing down, gravity is pushing down, and somewhere it gets to a point where the spring starts pulling up. And right in between these two areas, it's speeding up and then it's slowing down. And right in between speeding up and slowing down, that's where the max velocity happens. For accelerations, you can think of acceleration in terms of the force. As it gets to the top, it's really compressing this spring. The spring pushes down, and this is where the acceleration is pushing down the most. So max acceleration happens where velocity is 0. Up at the top and again at the bottom. This time we're pulling up, but it's going to be a similar magnitude. So we have an acceleration that's pulling this object up, and it's where the velocity goes to 0. So think about the relationship between acceleration and velocity. Velocity is 0, acceleration is maxed out here. Here's the center. What's happening in the center? We have gravity pulling down in the same amount the spring force is pulling up. This is the equilibrium position. All the forces add to 0. Acceleration goes to 0. So 0 acceleration, max velocity, max acceleration, 0 velocity. And we go through kind of this sinusoidal wave. Let's look at the graphs for this. Here's the position graph. This is graph versus time. So we're just following a wave. You can model this with either a sine or a cosine. If you compare the position to the velocity, so it falls and stops. The velocity curve is 0 here, where it stops. And then it picks up, that slope is getting steeper, steeper. The velocity is getting larger, larger, larger. Here's the largest slope, happens right in the middle. and then the slope starts getting shallower. It starts slowing down to, at the top, the slope is 0. It's stopped. The slope of the position curve, dx dt, that's your velocity. So you can see your velocity is 0, where this slope goes to 0, and over again. So where position is stopped, where the slope goes to 0, that's where velocity is 0. Here's a comparison of our position with our acceleration. The blue line is position again. So let's say we've stretched it all the way down. So at the bottom, our spring is all the way stretched out and it's pulling up. So the spring is pulling up. We have a positive acceleration where our position is at a minimum. And here we come to the very top. So at the very top, our spring is compressed. And the weight is being pushed down by this compressed spring up here. So negative acceleration. So the position and acceleration, these curves are mirror images of one another. So acceleration is a negative, where our compression is the highest. Okay, what other graph can we look at here? Here's all of them together. So blue line is the position of the weight just rising and falling, and where acceleration is the largest, that's where velocity is 0, and it stops right here at the bottom. So study these graphs, and if you can understand this system, you can understand just about any system and the relationship between those derivatives. So position, velocity, acceleration. Here's that equation again, and this time we're looking at acceleration as a function of position. It's negative, so that's that mirror image that you saw on the graphs. When position is up, acceleration is down. When position is down, acceleration is up. So we have that negative relationship. We're looking for a spring constant here. And if we want to find a maximum, we're looking for where other things go to a 0. So we have an equation here that is a function of x. Instead of a of x, we're just plugging in an equation over here, and we're going to have to know some boundary conditions, okay? Initial velocity, final velocity, where we don't have any compression, where's the maximum compression happening, and you're just going to plug through the calculus for this thing, okay? So v goes to 1/2 v squared, x goes to 1/2 x squared, and then you're going to plug in those boundary conditions to see the relationships between what the velocity is doing at those different positions, where the position is how much the spring is being compressed. If you plug this into Mathematica, so here we go. Here's a maximum velocity. When does our maximum velocity happen? The maximum velocity happens right in the middle in our equilibrium position, where the spring is not stretched out, it's not compressed, so right in the middle. And then our velocity goes to 0, where we're at a maximum compression for our spring. So at the very top, we're compressed. At the very bottom, we would be stretched out. So if we just plug in values for our maximum velocity, how much our spring is getting compressed or stretched out, that amplitude is the same either way. We can plug in the mass, and that means we know everything in this equation except for our spring constant. So we can solve this. We can go ahead and just plug everything in over here and solve for our spring constant. And that would be units of newtons per meter. So force equals kx, or k is going to be force per length. Okay, so there's our spring constant, and then once we know our spring constant, we can then calculate our accelerations. Now, where does our max acceleration happen? The max acceleration happens where the max compression happens. So we can just plug in that amplitude, or how much we're smushing that spring. We can plug in the spring constant we just solved for, and then we can get what the largest acceleration is, or we could solve for what the largest force is on here. So here's that last step. We're just plugging numbers into this acceleration equation where acceleration is a function of position. So acceleration, a function of position, this is what we're going to be integrating for those types of problems. So we did acceleration as a function of time, as a function of position. Last one and the hardest one, acceleration as a function of velocity. Another example problem. The acceleration of a particle is defined by a equals 9v cubed, where v is a velocity, a acceleration, and we're given some information. When time equals 0, x equals 1/9 meter, and velocity equals 1 meter per second. And what we want to find, so we want to find the velocity when x equals 1/5, and then we want to find the time when velocity equals 3 meters per second. So remember, there's two different scenarios for this one. There's one scenario where we're trying to relate this acceleration to what the time is doing, and there's another relationship we're trying to relate what the velocity and position are doing with one another. So for part A, this is position, velocity, and acceleration. So that's going to be position, velocity, and acceleration. That's going to be this one. And then when we start wondering what's happening time-wise, so time, velocity, acceleration, that's this equation. So just look at what variables you're trying to relate and find an equation that has the same variables in it. For part A, so part A is relating position, velocity, and acceleration. So we're going to be using this equation here. We have position, velocity, and acceleration. Plug in that equation we're given for acceleration. Group everything with velocities on one side, position on one side, and then just walk through the integration. And this is where, in some problems, depending on what equation you're getting, this integration can get a little bit messy because we have that equation down here in the denominator. Okay, so once we have, here's our final position, final velocity, initial velocity. We have everything related to one another, and then we can just start plugging in values. So initial position is 1/9, that's x naught, x at time 0 is 1/9, and at some later position, x equals 1/5, so there's our change in position. Our initial velocity is 1, so we're plugging in our initial velocity, and all we have left to solve for is what our final velocity is. So our velocity is 5. When our position is at 1/5, our velocity is at 5, according to these given conditions. Part B. This time we have time, velocity, and acceleration. So if you ask yourself, what equation are we using to relate time, velocity, and acceleration? That's this guy over here. Again, we're going to substitute in our equation for acceleration. So we have an equation for acceleration. We plug right in there. And then just crank through that integration. Use the math software if you don't want to do the calculus by hand. So we have v cubed, go to v squared. This is the final velocity, the initial velocity, and time. Here we go. So our final velocity is 3. Our initial velocity is 1. And we can just plug those values in and see what our time is. Here is some of your homeworks, and remember, you don't have to do all of these. I don't want repetitive, monotonous things, but let's just walk through what equations you would use in each of these scenarios, because you should think through each of these for studying for the test. Okay, so 11.3, and I did this example in Mathematica earlier. This is position as a function of time. So even though its position is a function of time and not acceleration is a function of time, we're still going to be using that v equals dx dt and a equals dv dt. So it's still going to be just those standard acceleration and velocity equations that we use for this one. Here's another one, acceleration as a function of time. And these are the most common types of problems you're going to see, is that acceleration with time. So we're looking at the first scenario here for each of these. We have something as a function of time, acceleration as a function of time, and we can also walk through and get acceleration as a function of time by just taking a couple of derivatives. So position to velocity to acceleration, we end up with an equation, acceleration as a function of time here too. Here's a couple of other problems. So in this problem, what do we have? We have acceleration as a function of position. A equals negative kx. So this is packing material. Packing material acts like a spring. So it's going to slam down into the ground, and that packing material is going to smush just like a spring. And this is true of most materials. Most materials deform just like a spring does, which is why those spring problems are so important. Okay, so if this is what we have, what equation would we be using? So A is a function of position, A is a function of position. We're going to be using these equations. So we'll just plug that equation in and integrate it. Here's another problem. So in this case, we have velocity and position. What would you do if you had a combination of velocity and position? And what we're asking for. So acceleration and position. We have time and position. For this case, we're interested in what's happening with the position. Now we're giving velocity in position, not acceleration in position. So we're going to have to go back and use this little relationship too. Okay? So where we have our velocity, we just plug that equation in for our velocity. Okay? And then instead of dv dx, we're going to take the derivative of that whole equation with respect to x. So just wherever you see a v in here, we're going to plug in our equation. So again, you just look at what variables you need to get related to one another. So we need to relate acceleration, velocity, and position. This is the equation that relates acceleration, velocity, and position. So just match the equation to the information you need to solve for. Wow, that's great if you're still here and actually listen to the whole thing. Again, take this slide, print it out, and put it in front of you when you're solving those homework problems, and just highlight what variables you have involved and match the equation to what you're trying to solve for. So acceleration, velocity, time, or acceleration, position, velocity, all different combinations here. But it all stems from just A equals dv dt and v equals dx dt. And then this is the last one, A equals v dv dx. That's the last piece of it. Okay, let me know what other slideshows and information you want to see. Let me know where you're getting stuck on this stuff. See you later.